Hi guys, it's Mrs. Allison. Today what we're going to look at is the last type of function that we'll use with Laplace transforms, and that is the Dirac delta function. So far we've learned about Heaviside functions, or like a switch that turns a function on for a certain amount of time and then off, and maybe it turns on several functions for set amounts of time. But we really haven't ever looked at a function that is like a force function. And so the Dirac delta function, and I'm going to use the word function loosely, is used to deal with this type of forcing function, to deal with a huge spike or shock in a large system at one moment in time. So the Dirac delta function is not truly a function like we think about, because if we looked at a picture of it, you would see it does not pass the vertical line test. But it's what we call a generalized function. Okay. The notation for a Dirac delta function actually uses the delta symbol, the lowercase delta symbol. And so we have this delta t minus a, or you could see it as this delta a, similar to that unit step function or the Heaviside function, where we have several different notations that mean the same thing. And really what it says, what this notation says, is that my function, delta a, delta subscript a, is equal to infinity at the moment of a, and it's equal to 0 everywhere else. So if we looked at a picture of this, let me make my pen just a little bit thicker so we can see it on there. If we looked at a picture of this, and let's call this mark right here a, then the Dirac delta function looks like this. It is 0 until we get to a. At a, we have a vertical spike up, and then instantaneously after a, it's at 0 again. So maybe think of this like a baseball being hit by the bat. The moment the bat makes contact with the ball, we have this force being exerted, and that is the Dirac delta function. Okay, so there's several properties that happen with the Dirac delta function. One, if we have delta of t minus a equals 0, then t cannot be a. The second one is that if we take the integral from 0 to infinity of this Dirac delta function, t minus a dt, it will equal 1. So at a, the area under this curve, if you will, no curve, but this area under this curve is 1. Okay, I'll write that down just so we can remember it. So this basically says that at a, the area is 1. And then the third thing that we have is that the integral from 0 to infinity of some function, f of t times this Dirac delta function, t minus a dt, equals f of a. And this comes from the idea of the mean value theorem for integrals. And we'll look at what this looks like here in just a second, but I want to talk about some of the bounds you could see. You could see these bounds going from negative infinity to infinity. You could see these bounds, let's write that down. So these bounds they could be the integral from negative infinity to infinity, but you may also see them as the integral from a minus some epsilon to a plus some epsilon. So just some distance surrounding a. They don't necessarily have to go from 0 to infinity, but if I want to say I'm going to let my epsilon be 10 and a is, I don't know, 10, then my integral would go from 0 to 20. Okay. Now, before we actually look at solving an initial value problem, what we need to do is consider the transform of the Dirac delta function. And what I'm hoping you see as we go through this are some properties that relate the Dirac delta to the Heaviside function. So if we look at our table of Laplace transforms, transform 4, so the Laplace transform of this Dirac delta equals the integral from 0 to infinity of e to the negative st Dirac delta t minus a dt equals, this is using the definition of Laplace. If we do this process, what we will end up getting is e to the negative as. We can see this as number 26 on the table. Okay, so let's take a look at an example of what this looks like. And these are fairly involved examples, just so you can be prepared to write small-ish on this example. So this says solve the following, I'm going to leave that formula up there, solve the following initial value problem, y double prime plus 2y prime minus 15y equals 6 times that Dirac delta function of t minus 9. Y of 0 equals negative 5, y prime of 0 equals 7. Now, if we didn't have, really, truthfully, a Laplace transform in this situation is going to be a little bit messier if we didn't have this Dirac delta piece, but we do. So let's go through and start solving. So we're going to take the Laplace transform of y double prime plus 2 times the Laplace transform of y prime minus 15 times the Laplace transform of y equals 6 times the Laplace transform of this Dirac delta function. Okay, so starting with that y double prime, I'm just going to go ahead and write this out. So we have s squared y, capital Y of s, the Laplace transform of y, minus sy of 0 minus y prime of 0 plus 2 times s, the Laplace transform of y, minus y of 0 minus 15 times the Laplace transform of y equals, and using number 26, this would be 6 times e to the negative 9s. Okay, so just like before, I'm going to substitute in my initial values, and then I'm going to group my like terms. So let's take that in 2 steps. And again, if you see it quicker, that's fine. This will be plus 5s, 5 and s again, minus 7, plus 2s Laplace transform of y, minus negative 5 times 2 would be plus 10, minus 15 times the Laplace transform of y equals 6e to the negative 9s. So, grouping our like terms, we would get s squared plus 2s minus 15 y, the Laplace transform of y, plus 5s plus 3 equals 6e to the negative 9s. And my guess is you can see where this might be headed. Yes, we are going to have some partial fractions, so that will be fun. So let's do some work with these partial fractions. I'm going to move everything over to the other side to get this Laplace transform by itself. So y of s equals 6e to the negative 9s minus 5s minus 3 over the whole thing factored. So s plus 5, s minus 3. And I'm going to clean this up a little bit just so we can do a partial fraction. Yes, you could do it from here, but I like to know what I'm taking my partial fractions of. And in fact, it looks like I'm going to have 2 partial fractions. Yep, that'll be fun. Okay, so here we go. We have, I'm going to separate this fraction like this. I'm going to pull out the 6e to the negative 9s over the s plus 5, s minus 3. And then I'm going to pull out a negative and make this positive 5s plus 3 over s plus 5s minus 3. Okay, so there are really 2 partial fractions here. The first one is this term right here. And what we can say about this Laplace transform, if I rewrite it here, is that really this expression is the expression 6e to the negative 9s times the Laplace transform. We're going to call this f of s. And so what I'm going to do is I'm going to come over here for just a moment, and I'm going to redefine f of s to be 1 over s plus 5 times s minus 3. And so I'm going to use my partial fraction calculator online. I'm not going to do this by hand. There's enough tediousness to this problem to not do your partial fractions. And when I do this online, we get that this fraction will be negative 1/8 s plus 5, and this one will be positive 1/8 s minus 3. So this is my f of s function. Okay, and then if I take the Laplace transform of just that portion, so the inverse Laplace transform, this lowercase f function will actually be negative 1/8 e to the negative 5t plus 1/8 e to the 3t. Okay, so if I rewrite this portion right here, I'm not going to rewrite that portion in just a moment. I'm going to show you a shortcut we're going to use. Let's look at this next part. Let's call this expression, and we're going to leave the minus there. So that minus becomes important. Keep that in mind. And I am going to consider this to be just a function g of s. And so I'm going to come to the side here, and you're going to do this. This is pretty common in these functions. I'm going to redefine g of s over here to be the 5s plus 3 over the s plus 5 s minus 3. And that gives me a over s plus 5 plus b over s minus 3. And again, using my partial fraction calculator, I get that this function, this is g of s, is 11/4 over s plus 5 plus 9/4 over s minus 3. So my g of t function is going to be 11/4 e to the negative 5t plus 9/4 e to the 3t. Now, there's a very strategic reason why we would do it this way, why we would separate these. Because I know now, going back to my original problem, I would now need to take, this is where I would need to take my inverse Laplace transform right here of this expression. Okay? And when we do that, what we end up getting here is we get 6, oops, I don't want to be in a highlighter. We get 6, and if I remember my Laplace transforms, we notice that this expression right here, the inverse Laplace transform, is really the unit step function. And with that negative 9, this would be the unit step function of 9 of t. And then because we're taking the Laplace transform of this, but my step is at 9, this would need to be f of t minus 9. Okay? And then with that g of t, or g of s, the inverse Laplace of that is just going to be g of t. And so the beauty of this is I don't necessarily need to go back and redefine my functions. I can simply say where f of t and g of t are defined at right. So my f of t right here, my g of t right here. Now, let me scroll up just for a moment, and I'm going to show you what it would look like if we didn't just simply define them that way. If we went ahead and substituted those back in, given that this first part is my unit step function, and this needs to be f of t minus 9, what I would have here is negative 1/8 e to the negative 5t, but t needs to be t minus 9, plus 1/8 e to the 3 would be t, but it needs to be t minus 9, minus, let's see if I have room, 11/4 e to the negative 5t, plus 9/4 e to the 3t. And this would be my function, my y of t. I lost my y of t up here. So this is my answer. So it's a little bit more involved, and we get some interesting results with this Dirac delta function. So let's hit pause and in the video and have you try the next example and see how you do. All right, so now we had a chance to try this one. So my first setup is I'm going to take the Laplace transform, or 2 times the Laplace transform of y double prime, plus 10 times the Laplace transform of y, equals 3 times the Laplace transform of, we've got some fun stuff going on here. We've got the unit step function at 12, minus 5 times the Laplace transform of the Dirac delta function, okay, so moving from here, we have I'm going to go ahead and substitute in my y of 0, so this would be times -1, minus y prime, which will be plus 2, plus 10, Laplace transform of y, equals 3e to the negative 12s. Did I get all that? Yes. Minus 5e to the negative 4s. Nope, this should have a divided by s. Okay. Not sure why I have 2 s's here. So minus 4s. Okay, so let's start grouping like terms. All right. There we go. So now we've grouped everything that's alike, and I am going to go and divide both sides so we can get the Laplace transform of y by itself. So we get 3e to the negative 12s over s times 2s squared plus 10 minus 5e to the negative 4s over 2s squared plus 10, and then minus 2s plus 4 over s squared plus 10. And then I have 3 functions I'm going to focus on. So I'm going to move this over, and I'm going to go ahead and start with this first one. We will call this function, if I rewrite this y, the Laplace transform of y, I would have 3e to the negative 12s times, let's call this function the Laplace transform of f. On the next one here, we would have minus 5e to the negative 4s, and then this would be times the Laplace transform of some other letter, let's call it g, of s, and then we have minus, and this one we can use by itself, so we'll just give this the name h of s. So now I'm going to go and do the work for each of these independently. So let's start with f of s. We have 1 over s times 2s squared plus 10, which means I have a over s plus bs plus c over 2s squared plus 10. And I'm going to use my calculator on this. I'm not going to do the work by hand or Symbolab or whatever you're going to use. 1/10 over s plus negative 1/10 s over s squared plus 5. And so when I do the inverse Laplace of this now, of this expression now, then what we get is we get f of t is going to be 1/10 minus 1/10 cosine of root 5t. All right, let's work on the g of s function. So we have 1 over 2s squared plus 10, which I don't actually have to do a partial fraction on this, although I do need some work. So I'm going to pull out a 1/2, which leaves me with 1 over s squared plus 5. And this doesn't quite fit any patterns because the sine function happens to have the like term in the numerator. So I'm going to go ahead and rewrite this as 1/2 times root 5 over root 5 times s squared plus 5. And so then really what I get is 1 over 2 root 5. Let's change how I write this. It's not wrong. You could keep going. But I was just already doing the inverse Laplace transform, and that notation is wrong. So this is my g of s. If I do my inverse Laplace transform here of this expression, then we get g of t is going to be 1 over 2 root 5 times the sine of root 5t. And then the h of s function is going to be 2 times s plus 2 over, oops, I think I lost the 2. 2s squared plus 10. I did. So let's go back here real quick. So back over here, I just lost the 2s squared. So that should have been a 2s squared. And right here, I'm going to go back to this, and I'm actually going to factor out a 2 to leave me with s squared plus 5. And so really what I have is s plus 2 over s squared plus 5. And I could separate this into s over s squared plus 5 and 2 over s squared plus 5. And this first fraction, no problem. We can take the inverse Laplace transform of that one. But for this next one, we would need to rewrite this as, like, take a root 5 over root 5 here. And so if we do the inverse Laplace transform now, what we get is h of t is, this will be the cosine of root 5t, and this one will be 2 over root 5 times the sine of root 5t. And again, you can see why maybe plugging these back into this function would be easier not to. And so what I get now is, if I take the inverse Laplace transform of this expression here, I ran out of room. If I take the inverse Laplace transform of this, I end up with 3 and the unit step function at 12, which means this needs to be f of t minus 12 minus 5 times the unit step function u of 4, which means this would need to be g of t minus 4 minus h of t, not a unit step function there. And then I can just say where f of t, g of t, and h of t are defined at the right. If you wanted to make note of them, it might make your life easier. And so then this would be my y of t function. And we're done. Hopefully did okay on those. All right. Now, before we finish with the idea of the Dirac delta function, really no math is different other than just looking at a different Laplace transform. The steps to get there can be a little bit messier just because of the nature of that function. But before we go on, let's look at how we can relate the Heaviside function and the Dirac delta function. So if we take the integral from negative infinity to some value of t of this Dirac delta function of u of minus a du. So I'm taking the integral with respect to u. This is going to equal a piecewise function that equals 0 when t is less than a, but equal 1 when t is greater than a. Okay, that's the definition of the Heaviside function. So what we can say is we can say that the integral from negative infinity to t of this Dirac delta function with respect to u is equivalent to the unit step function where the step is at a of t. And if we look at the fundamental theorem of calculus, we get that if we take u prime of this unit step function, what we really get is the derivative with respect to t of this integral from negative infinity to t of the Dirac delta function. And then we can say that that is equivalent to the Dirac delta function evaluated at t minus a. And so really what we can say is that the derivative of the Heaviside function is the Dirac delta function. This is a pretty cool relationship. So there is a relationship between the Heaviside function and that Dirac delta function. All right, so you have a worksheet that goes along with these notes. You do have a unit test coming up, and I left notes for the sub on that. So have a great day, and we will talk to you soon.